All right, so what we want to do today, to start off with, is to continue doing some theory from chapters 4 and 5 on continuous random variables for chapter 4, and then a little bit of bivariate multivariable random variables in chapter 5. But the main thing I want to do after we do some of that is do some simulation. So we'll start with some simulation in a spreadsheet. We'll move on to simulation in Mathematica. Hopefully at some point I do want to do some R. I want to start with some basic statistics kinds of things in R, maybe some basic graphs. Maybe we can figure out to do some simulation as well. To start the theory for today, I thought we could do an exercise together. And here's the exercise. This is actually a pretty important little exercise. Suppose you've got a standard normal random variable. You know, we usually call that Z, right? Z is the standard letter for standard normal random variable. Normal with a mean of 0 and a variance and standard deviation of 1. Our book always, well, in all books, typically call that first number the mean, mu. Our book calls the second number the variance, sigma squared. You should be aware that other books label that as the standard deviation. However, when it's 1, it doesn't matter. The variance and the standard deviation are the same when they're both 1. What I want to show, well, okay, instead of showing something, let's explore or ask a question. What is the distribution of Z squared? So Z has a standard normal distribution, a standard normal random variable. Its PDF, its density, is a bell-shaped curve. Centered at 0 with a standard deviation and variance of 1. And I hope you remember that means the inflection points of this graph are 1 unit away from the mean. So they would be at plus or minus 1. You'd also have things like the 68, 95, 99.7 rule. 68% of the area is between -1 and 1. 95% of the area approximately is between -2 and 2, within 2 standard deviations of the mean. About 99.7% is within 3 standard deviations of the mean, between -3 and 3. What are we doing when we say consider Z squared? Are we like squaring this PDF or something? No. You're imagining squaring the outcomes of the random variable Z. What does that mean? Well, think about it. If this is modeling data, the fact that the density is highest near 0 means the majority of your data would be clustered close to 0. In fact, about 68% of it will be between -1 and 1. About 95% will be between -2 and 2, etc. But the higher the PDF is, the higher the density is, the more dense your data will be. Of course, to really see dense data points, you'd have to have lots of them, probably like thousands of data points or something like that, to really see the density. If you made a histogram for these data, a bar chart, it should have this kind of shape. It should be densest, the highest frequency near 0. It's those values you need to imagine getting squared. Now, those values are both positive and negative. When you square them, you're not going to get a negative number, right? No imaginary numbers here. So whatever the distribution of Z squared is, it can't take on negative values. And since the majority of the data is close to 0, like between -1 and 1, when you square them, those numbers are still close to 0. In fact, between 0 and 1. So whatever the distribution of Z squared is, it should have a density that's positive, not negative. It's going to take on values of 0 when the input is negative. Relatively high between 0 and 1, and relatively low greater than 1. Does it do something like this? I'm not going to actually draw it yet. Does it do something like this, perhaps? Or does it do something like this, perhaps? That's not so clear. See what I just did? Does it do something like this? Or does it do something like that? That's not so clear. Let's see if we can figure it out. How? Well, let's give this quantity a name. Let's call it y. Turns out to be easiest in determining the distribution of y to find its CDF first instead of its PDF. CDF of y is an easier thing to figure out. What should I call it? Well, how about capital F? Maybe capital F sub y, sub capital Y of little y. Why are we doing this? Well, for one thing, it's of theoretical importance. For another thing, it's going to lead us towards simulation, actually, with another example. The CDF, remember, I did mention this last Thursday, is always, 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 always the probability that the given random variable is less than or equal to the given value. It's always the case, whether your random variable is discrete, continuous, or mixed. Some mixture of discrete and continuous. We're not going to talk about mixture today, but we probably will on Thursday. This is always true. The way you compute it is different, depending on whether it's discrete, continuous, or mixed. If it's discrete, you compute this as a summation. If it's continuous, you compute this as an integral. And if it's mixed, well, that's not so clear at the moment. Maybe some sort of combination of summations and integrals, maybe. I'm not going to actually compute it as an integral here. I'd like to think about it theoretically. What should I do? Well, I better use what I'm assuming somehow, right? I'm assuming z is standard normal. I better use that. How? Well, I'm saying y equals z squared, so go ahead and replace y with z squared. Z is standard normal. How can I relate this now to z itself, not z squared? What do you think I should do? Got a guess? Take the square root. However, in taking the square root, you do have to be careful. Z can take on positive or negative values. Z is standard normal. To say z squared is less than or equal to little y, where little y is greater than or equal to 0 here, is really to say that z itself is between negative square root of y and positive square root of y. Right? If z squared is less than or equal to 4, that means z itself is between -2 and +2. If z squared is less than or equal to 9, then z itself is between -3 and +3. All right. So now should I go like to a standard normal table or something? Help me solve this? Well, you could if you knew what y was, but y is a variable here, so it's not so clear. I could use the symmetry of the normal curve about 0 to say this is 2 times the probability that z is between 0 and square root of y. That would be symmetry by symmetry. And that makes it a little easier to think about, perhaps. Perhaps. Actually, yeah, that'll be a little easier. let me write the CDF of Z in its actual usual form that people use outside of our textbook. The CDF of standard normal random variable, I think I mentioned this last Thursday, is typically written as capital phi. That's the standard notation for the standard normal random variables CDF. And the probability that Z is between 0 and square root of y can be written as the difference of CDF values, right? Why does that work? Well, intuitively it works because you're thinking of the area under the graph from 0 to square root of y, this area right there. You're thinking of it as the area under the graph to the left of square root of y forever, minus the area under the graph to the left of 0 forever. And actually, by symmetry, this is 0.5. I know that's 0.5. So ultimately, we can actually write this as 2 times capital phi of square root of y minus 2 times 0.5 is 1. I could write ultimately the CDF of capital Y in terms of the CDF of a standard normal. Capital phi is the CDF of standard normal. That is standard notation that many, many people use, many, many books use. So I could write the CDF of Y like that. Is that helpful? Do I know the formula for the CDF of standard normal? That involves ERF. Remember ERF? Error function. It's not an elementary function, not a function you're used to. The new function. So I can't really simplify this anymore, it seems, without using ERF. However, I do know the formula for the PDF of a standard normal. Right? It's in chapter 4, it's in the table. It involves E. By the way, exp essentially means E to the whatever that is. Just shorthand. Actually, it's not really shorthand, it's typographical reasons they put an exp there. So that when you got this, if you wrote it as E to this humongous power, then it gets hard typesetting wise. So exp of something means E to that something. Exp stands for exponential function. That's the PDF. And if mu is 0 and sigma is 1, it simplifies a lot. So, maybe I should try to find the PDF of Y now. Maybe I should differentiate this. This is a pretty important technique that I'm showing you here, including for applications, including for simulation. Little f sub capital Y of little y, the PDF of capital Y, by definition in the continuous case, is the derivative. Because this is a continuous random variable of capital F. I forgot to put a prime in there at first, now it's there. Capital F sub y prime of little y. So differentiate this thing. I got a square root of y in there. I guess I need the chain rule. -1 differentiates to 0, so that's not a big deal. The 2 stays there. 2 times the derivative of capital phi evaluated at square root of y. Then by the chain rule, what's the derivative of square root of y? 1/2 y to the negative 1/2. The 2's cancel actually, and you're left with capital phi prime of square root of y divided by square root of y. Capital phi prime, though, is this function when mu is 0 and sigma is 1. Let's write it as e to a power. I'll bring this 1 over square root of y out in front. 1 over square root of y times, from the table, it's 1 over square root of 2 pi e to the negative x minus 0 squared, which would be just negative x squared. Or, excuse me, sorry, mistake. Scratch that out. 1 over square root of y times 1 over square root of 2 pi e to the negative, yes, x squared if the variable were x, but I'm replacing x with square root of y. So it's square root of y squared over 2 sigma squared. And sigma is 1. So this is the PDF of y. Y is positive here. Remember, initially I said y is greater than or equal to 0, though remember with continuous random variables, it doesn't matter whether you use strict inequalities or non-strict. Here it kind of made sense to say y could be 0, but with this formula, y can't be 0. Is it really a PDF? We should probably check it with Mathematica. Do that up here. It should integrate to 1, right? Zero to infinity. 1 over, I guess I could do all the square roots together here. 2 pi times y e to the, use a capital E, negative square, okay, I could simplify it a little bit. This would be negative y, square root of y squared would be y. Negative y over 2. 1, yay. Yeah, it simplifies a little bit. And in fact, I'm even going to rewrite it a little differently. Actually, rewrite it even differently. 1 over square root of pi. I'm going to write the square root of 2 as 2 to the 1/2 separately like this. And I'm going to write 1 over square root of y as y to the negative 1/2. And then I will simplify the exponent there to be e to the negative y over 2. Why did I do that? Because this is actually a familiar PDF. I'm sure you didn't memorize it, but it is actually in our friendly table, our friendly neighborhood table. Same table, chapter 4. This function right here is, can't get them all on this, okay. Is the same as, or at least very similar to this function, chi-squared. Can you see it? Is that big enough? You can look in your book if you like. Page 136. Right there. Except a y instead of an x. We got an e to the negative y over 2. We got a y to the negative 1/2. That's going to fit this pattern if the little gamma is what? 1. 1/2 minus 1 would be negative 1/2. We got to divide by 2 to the 1 over 2, 2 to the 1/2, square root of 2. Oh, does that mess things up? Capital gamma of 1/2. Is it square root of pi? Mathematica, what is capital gamma of 1/2? Square root of pi. Yeah. Wait a minute. Isn't the gamma function the factorial function? Gamma of 6 is 5 factorial. Gamma of 7 is 6 factorial. Remember that? What? How could you gamma of 1/2? What is that? Negative 1/2 factorial? Can mathematics even do that? I guess so. What? What? The gamma function is defined for other values of the input besides positive integers. And it can give you weird things like this. It's defined in chapter 4 using an integral, a very strange looking integral. Oh, where are we? The capital gamma function is this function of alpha. And I guess you're allowed to plug in alpha equals 1/2 into that, and I guess you would get square root of pi for that integral if you did. It's not clear why. You could look into it if you're interested. We're trusting Mathematica here. We have a chi-squared random variable here with little gamma 1 degree of freedom. Little gamma was the degrees of freedom. That's what this is. That's the result. What is the distribution of z squared? It's chi-squared with 1 degree of freedom. That's what it is. And that's actually important for us in this class to know that. If you square a standard normal random variable, the result is a chi-squared random variable with 1 degree of freedom. So our result here, and Dr. Wetzel like to use to call these things results rather than theorems because we're not really being careful in how we state these things. Result if z is standard normal, that implies z squared, I guess you could write it like this, is chi-squared with 1 degree of freedom. That's not an x there, that's a Greek letter chi. It, of course, looks like an x, but we call it chi. I was always used to calling it chi-squared, but many people call it chi-square. Why? I looked it up. It's because you're not literally squaring anything with this. You are squaring that. Maybe that's the origin of the name, but you're not literally squaring the symbol. So for that reason, some people call it chi-square. I always learned when I was younger, chi-squared. It's not a big deal. About to do a similar example, similar in style. That's going to be important, super important for understanding simulation. Simulation of continuous random variables. Okay, so partially I did this example because it's just important in general for some applications later in the course. Partially I did this example because it's going to be practice for us. For the next example, another exercise. I'm calling these things exercises, but I could call them examples. And this exercise or example is going to be important for simulation. Let x be a continuous random variable with CDF capital F sub x of little x. And suppose I've got a new random variable. I'm going to call it u instead of y this time. That equals capital F sub x of capital X. I guess I'm calling these exercises because I'm ultimately asking them as questions. The question is, what is the distribution of u? Yeah, so this is these two exercises are examples of transformations, transform random variables, which the book does talk about to some degree at the end of chapter 4. And I did put it on Moodle, though kind of late. I put it early this morning on Moodle to read the end of chapter 4 as well as chapter 5. I should have done that earlier. At the end of chapter 4, there's a section about, well, there's two sections that we don't cover in Prob and Stats. So actually 3 sections we don't cover. There's one about transformations of random variables and another about simulation. The one about simulation is much shorter. The transformation is kind of long, kind of confusing. What I'm showing you here in these exercises is kind of the heart of that section about transformations, but I'm doing it in really what's an easier way. The harder way, a bit more confusing, involves derivatives in the abstract, derivatives of inverse functions, in fact. I am using derivatives like I did here to find a PDF, and I will do here as well, but I'm not stating the method in kind of an abstract way, which is the confusing part. I'm doing really what you would call the CDF method. Let's first find the CDF of U. Just like I started this example by finding the CDF of Y. Not saying what X is. So whatever I'm about to do is going to be an abstract thing because I'm not specifying what capital F is. The CDF of capital U, I could call it capital F sub U of, say, little u. By definition, as always, CDF is the probability that the random variable is less than or equal to the given number. That's always the case. This is essential to realize this week. Today and Thursday, we're going to use this idea a number of times, and it'll probably go into next week some too. All right, what do you do with this? Again, here's how the light bulb goes off in your head. I better use what I'm assuming. I'm supposing U equals that. I better use that somehow. How? Well, I guess the only thing to do is replace the U with this CDF of capital X, evaluated at capital X, replace U with that. I guess that's the only thing you can do. Where in the world am I going with this? Got any bright ideas? What did I do in the last one? The last exercise, I was to this point here. And then I essentially tried to rewrite the inequality in terms of Z to help me use the capital phi, like CDF of a standard normal. Could I do something similar here in the abstract? Could I, for example, somehow isolate capital X? Get rid of the capital F sub X somehow, sort of? No ideas? It's abstract. Could I do something like this? And if so, what would I put there? U? The answer is no. I would not put little u, though it would involve a little u. No ideas? When you try to solve an equation like this, e to the x equals 5, what do? Take the natural log of both sides, right? ln of e to the x equals ln of 5. In other words, x equals ln of 5. What's the relationship between e to the x and natural log of x? They are inverses, inverse functions. You could pretend capital F and maybe is e to the x or something, maybe. It wouldn't be actually, but to get x isolated, you would take the natural log, the inverse function of both sides of the inequality. Yeah, that's what we do in the abstract. Write a capital F sub x over here, but with an inverse symbol. That's not -1 power, that's inverse function. Oh, wait a minute, can I really do that? Does F inverse exist? How do I know it exists? Wouldn't capital F sub x have to be 1-to-1? 1-to-1. Is it? It actually depends on what the CDF is, actually. CDFs, remember, are always non-decreasing functions. Sometimes they're always strictly increasing, but sometimes they can be constant for a while. Well, let's not worry about it too much. Let's just assume we're kind of in the case where the graph of the CDF is always strictly increasing. So you'd have to think about the technicalities of whether this would really work in the case where capital F is sometimes constant, which it can be. And just pretend its graph is always going up. Assuming capital F sub x is monotone increasing. It's certainly non-decreasing. It doesn't go down in value, but it can stay constant sometimes for a while. And assuming if it's monotone increasing, then the inverse function is going to exist. And what's going on here? Hey, wait a minute. What's the CDF of capital X? The CDF of capital X, by definition, capital F sub x of little x is the probability that capital X is less than or equal to little x. That's the CDF of X. See the similarity there? P of X less than or equal to something. This is a value of capital F sub x. What value? Capital F sub x of whatever's over there. I guess that's capital F sub x inverse of u. But wait a minute, fx and fx inverse are inverses. This gives you u. Hey, that's pretty simple. And what's the PDF of u? Its derivative. Little f sub u of little u is the derivative of capital F sub u of little u. And that's going to be 1. Wait a minute, how can a PDF always equal 1? Can a PDF always equal 1? It's a bit of a trick question. Can it be a horizontal line for its graph? Yeah, as long as it's only 1 for a limited range of values, like from 3 to 4, or from 7 to 8. In fact, it would have to be a 1-unit interval of values, 0 to 1 maybe. And actually, in doing this calculation, since capital U is the CDF of capital X evaluated at capital X can take on any real value possibly, but U can only take on values between 0 and 1. CDFs do have to be between 0 and 1, right? Their outputs have to be between 0 and 1. You know, a typical kind of graph of a CDF might look like this. At least if it's monotone increasing. Might look like that. And the outputs are between 0 and 1. They have to approach 1 as the input goes to infinity. U has to be between 0 and 1. Little u has to be between 0 and 1 here. I'll put less than or equal to's, but I could have put strict inequalities. Less thans. Doesn't matter with continuous. And yeah, this u's, hey, that's why I called it U. It's a uniform random variable. Uniform distribution. You had an exercise about uniform distributions over the interval from A to B, right? The graph of little f is up at 1 when U is between 0 and 1 and is 0 elsewhere. And again, it doesn't matter whether I have open circles down on the axis and closed circles up on top, or open circles on top and closed circles on the bottom. Doesn't matter. It's a continuous random variable, so you're never going to observe a value of exactly 0 or exactly 1 anyway, right? These things are models of reality, so rounding, you could round to 0 or round to 1, but in terms of real numbers that have infinite decimal expansions that go on forever and ever, getting exactly 0 or exactly 1 is impossible. Getting exactly any value is impossible, which again, that's the paradox. But of course, we do observe values, but they're really rounded values, so they're really values with a margin of error. It's confusing, yes. Try to dispel the confusion by talking about it again every so often. So the result is that for any random variable X whose CDF at least is monotone increasing, U is going to be uniform 0, 1. Now I could write U of 0, 1, but that would be confusing. Maybe I should do UINF 0, 1. What if the CDF of X was not monotone, strictly increasing? What if it's constant sometimes? Well, then it's not so clear if this is going to work. But maybe it sort of works still. Maybe. Not going to worry about it at the moment. Okay, what I'm going to do next is go on to chapter 5 a bit. We have got 35 minutes left. I do want to do some simulation too. So I'm not going to go into super depth in chapter 5, a super amount of depth right now. We'll continue talking about it more on Thursday. But let's get some of the basics down. In the case of bivariate random variables, chapter 5, we could generalize this to multivariate random variables, trivariate, quadvariate, quintvariate, hexvariate. What am I saying by bivariate? I'm saying it's a two-dimensional random variable, if you will. You could write it as a point, capital X comma capital Y. If it were trivariate, it would be three-dimensional. I have a point that would have 3 coordinates, X, Y, Z, say. In general, you could talk about an n-dimensional random variable. That's like a vector with, or a point with n coordinates or components. The language is not consistent. As usual, this can be discrete or continuous, or maybe mixed. Mixed here, it sounds difficult. There's the discrete case and the continuous case. In the discrete case, we've got your joint PMF, probability mass function, which we could call little f sub capital X, capital Y. I'm not multiplying capital X and capital Y when I write that. I just don't feel like using the parentheses and the comma because it's just getting too unwieldy. I'm not multiplying there. It's a function of two variables, little x and little y. By definition, it is the probability that capital X equals little x and capital Y equals little y. Now, if capital X and capital Y happen to be independent random variables, which I haven't defined technically speaking yet, it would turn out that this is the product of the probability that X equals X with the probability that Y equals Y. In other words, it would be the product of the marginal PMFs of capital X and like capital Y. Remember, marginal. If X and Y were independent, using the multiplication rule for independent events in chapter 2. Usually they're not going to be independent. In fact, the main way to make random variables independent is to define them to be independent by setting their joint PMF, in the discrete case, equal to the product of their marginal PDFs. They're individual PDFs if you prefer, instead of marginal. In the continuous case, we do have a joint PDF, which I could still denote by the same way, little f sub xy of little x comma little y, but that value is not a probability, it's a probability density. And you've got to find probabilities by integration. Integrating the simplest kinds of probabilities in this situation is to integrate over rectangles. Say capital X is between A and B, and capital Y is between C and D. This doesn't equal the PDF value. It equals the integral of the PDF. In the abstract, you'll see people write D capital A here. But if we're integrating over a rectangle like this, we can just go ahead and put limits of integration right away. Say, let's do dy dx. So the inner integral is with respect to y, going from C to D, and the outer integral is with respect to x, going from A to B, though you can change those around. That's an equality. That gives you that probability. You can do more complicated probabilities over triangles. The point xy varies over a triangle, or even some weird shape, though the calculation could get hard or maybe even impossible if you do. You can still approximate the integral with numerical methods. Approximate the volume under the surface graph. So what are the marginal things? Marginal PMF in the discrete case, there's a little f sub x of little x and a little f sub y of little y. This is the probability that capital X equals little x. And to calculate it, if you've got the joint PMF, you add up values of the joint PMF over all y. And for the other one, it's a symmetric kind of thing. Add up values of the joint PMF over all x. Kind of abstract, but that is what you do. And the way it works out in practice is you either have formulas for the joint PDF and you point PMF and you do these summations based on those formulas, or you maybe more commonly have a table of values for the joint PMF. like this. The numbers in the main body of the table are the joint PMF values, probability mass function. The values down here and over here are marginal PMF values. To find this 0.9 there, you add across the row. That's a value of a marginal PMF of X. Add up the joint PMF values as Y varies, in this case from 0 to 3, when X is 0. For this next 1.08, add up the values in that row, etc. For this joint PMF, this marginal PMF at X equals 0, add up these values as, this is Y equals 0, excuse me. Add up these values as X varies from 0 to 2. X goes down, Y goes across here, which is the opposite of the usual, but that's the way it's set up. For the continuous case, surprise, surprise, you find these marginal PDFs now by doing integrals. And it's simplest to just write minus infinity to infinity. Though, of course, your joint PMF might only be positive over some finite interval, and so you could typically simplify. You don't typically have to do an improper interval. For the marginal PDF of X, you are integrating with respect to Y, and for the marginal PDF of Y, you are integrating with respect to X. You're trying to make the Y go away by integrating with respect to Y. Here, you're trying to make the X go away by integrating with respect to X. Here, you treat the X as fixed when you do the calculation, but at the end, hey, you say, my answer depends on X, so now I'm going to think of X as a variable. When you do this one, you treat the Y as fixed when you do the calculation, but then in the end, your answer depends on Y, and so then you can think of Y as a variable. Same kind of idea over here. There's also conditional PMFs and PDFs. I guess I should do F's here, and this is marginal PDFs. Conditional. Conditional, I spelled that wrong. Conditional PMFs. For example, there's F sub X given capital Y equals little y. Sometimes you just write the little y there instead of capital Y equals little y. This is ultimately a function of little x, though. You think of the little y as fixed, and think of this as a function of little x. And the formulas I'm about to write are the same, whether it's it's the discrete case and it's PMF, or the continuous case and it's a PDF. These abstract formulas work in both cases. The way you calculate them is different, but the abstract form is the same. This is supposed to be probability-wise a conditional probability, so it's a ratio. It's the probability that capital X equals little x and capital Y equals little y divided by the probability that capital Y equals little y, because that's the given information. This is like conditional probability from chapter 2. But that's the ratio of the joint PDF, PMF/PDF, divided by the corresponding marginal PMF or PDF, depending on whether you're in the continuous or discrete case. And we can do it the other way around too. The only difference is you divide by something different. The top is the same. Oops, it's an X, and this is supposed to be an X. an X there. In abstract form, these work both in the discrete and continuous case. The way you compute them is different. Discrete case, summations, continuous case, integrals. Actually, you only have to do the summations and the integrals for the bottom because the top is already given at the start of the problem. You can do expected values. I'm not going to write these things down. Expected value of X, if you're given the joint PMF or PDF, or PMF and PMF case, is the summation over both all X's and all Y's of X times the joint PMF. For the expected value of Y, it's similar. In the continuous case, it's similar. Instead of summations, you have integrals. You can define general expectations of functions of two variables, h of x comma y, in both the discrete and continuous case, in the way you would guess if you were forced to guess. And ultimately, you can also define not only expected values, not only means, but also something called the covariance, which is the analog of the variance. Variances can't be negative, covariances can be negative. This is the definition of it. However, just like with variances, there's a computational formula. This one. I'm rushing through this because I want to get to the simulation. Okay, you should read this. And then we have this theorem, but unfortunately is only one directional. If X and Y are independent, then this is true. The expected value of X times Y is the expected value of X times the expected value of Y, which would mean ultimately the covariance is 0. However, it does not go the other way. Just because these are equal does not mean X and Y are independent. That's very unfortunate, but it's what we're stuck with. And the book gives an example illustrating why that doesn't work. We'll talk about chapter 5 more on Thursday. But for the remaining time, let's talk about simulation. So you can do simulation in a number of ways. And the way you do it often depends on whether your variable is discrete or continuous. Let's do a discrete example to start off with. And let's do it in a spreadsheet to start off with. So I'm probably going to, I will share the spreadsheet with you. I'm probably going to assign one problem doing a spreadsheet simulation. Why don't we simulate the content of, or talk about simulating at least the content of one of your exercises for today. From chapter 3, actually. It's a binomial random variable. What was it? Not that one. Last problem, I think. Metal detectors in airports. Assume each time a metal detector at an airport signals, there's a 25% chance, probability, that it's because of change instead of like a pocket knife or something. During a given hour, 15 passengers are stopped because of a signal from the metal detector. Part A was to find the probability that at least 3 people were stopped due to change in their pockets. Part B would be unusual if nobody was stopped because of change. So you're trying to find probabilities for binomials, binomial random variables. And I hope you remembered how to do that or figured it out. You could use your calculator, that kind of thing. Let's use a spreadsheet to do it. You could have used a spreadsheet as well. Maybe you did it this way. Let's say, what do we have here? We have X is binomial B with N, the number of trials, equal to 15 people, and the probability of success was 0.25. B n comma p is a standard way to represent shorthand for binomial distribution with parameters n and p. N is the number of trials. P is the probability of success on each trial. And remember, X counts the number of successes. Success here in this example means they have change in their pocket. The metal detector went off because of change in their pocket. Let's build both the probability mass function, PMF, and the CDF for the different possible values of capital X. Little x could be 0, 1, 2, 3, etc. We can use spreadsheet formula to save some time here. I can do that. X could be as high as 15. Oops, sorry. How about the PDF values? Little f of x equals probability that capital X equals little x equals binomial. Yes, we'll do it. The syntax is to put, first of all, the number of successes first, I believe. This question mark will confirm. Yeah, number of successes, that's the value of X. Number of trials, that's the value of N. Probability of success, that's 0.25 here. And for a PMF, it's not going to be cumulative. In the cumulative spot, either put a 0 or put the word false. N is 15, probability of success is 0.25, false. Or 0, 0 representing false. Click and drag this down to copy and paste. There we have it. There are the probability mass function values in this situation. Where should they be highest? Don't look. N is 15, P is 0.25. Where's the mean going to be? Around 4, 3 or 4. Highest values, that's not the same as the mean. The mean is N times P, 15 times 0.25 will be what, 3.75? Mean is the center of mass, which is affected by the possibility of high outliers here. The mode, there's two modes actually, 3 and 4 have the highest probabilities and they're equal. If there was just one value of X that gave you the highest probability, that would be the unique mode. It's not, I mean, there's two modes, but it's not really bimodal in the usual sense. It's still sort of one peak. It's just combined with the values of 3 and 4. I could make a histogram of this. We could also figure out CDF values, capital F of X. And I could do the same kind of syntax here and just put a true at the end instead of false for cumulative. But it's maybe more fun to use a formula and to think of the CDF as the sum of PMF values. So the first value is just the same as the PMF value at 0. For the next one, I could just type this plus that. And then if I copy and paste that formula, it will get updated correctly. So yeah, 0.08 is about 0.013 plus 0.067. 0.08 plus the next one of about 0.156 will be up to 0.236 or so. And out on that one, we'll be up near 0.46. Add on this one, you'll be up near 0.686 or so. Yep, okay. And then we eventually get to 1. Okay, what do you do for simulation? We could look at the CDF values. We could round these things. And maybe I should have picked a different answer, where different problem where n wasn't so big. Let's round these to say say 4 decimal places. Because of rounding, the last 5 of them round to 1.0000. So effectively, in my simulation, I'm going to sort of lump all these together. They're so rare. Just going to lump them together. And how would you simulate? You could think of it this way. Analogous to the table of random digits that the book talks about. You could let, say, I'm going to use 4 digits, 0000 through 0133 is going to represent the outcome x equals 0. Why did I pick 0133? Because there's a 0.0134 there. If I'm starting sort of with 0000, this group of numbers effectively representing the numbers 0 through 133 with 4 digits is actually 134 digits. So this, I should probably copy and paste that down a little. This represents the outcome of 0. You could do it from 0001 to 0134, but the problem with that is once we get to 10,000, that's not a 4-digit number. We want to go to 9,999. The next, well, how many? From 0134 to, what would it be? It's a little tricky here. We want 802 minus 134 digits in there. 802 minus 134. We want 668 digits in this range. 0134 is already included. So I actually would have to add 667 to 134. 134 plus 667. It brings you to 801. And if you include all those digits, there are 668 of them. That represents getting the outcome of 1. Where am I headed with this? I'm not going to completely fill in the table, but what you would want to use now is equals random integer. It's not the only way to do this. Say 0,9999. Oh, I thought it was random integer. I thought that was what it was on a spreadsheet. Random. Or maybe rand. No. Oh, yeah, I know what it is. I got confused. It's equals RANDBETWEEN. 0 to 9999. I happen to get 6505 that time. That in this category. So that's representing an outcome of getting 1 success. I made a mistake, didn't I? Not 668.
6505.
Okay, it's not in there. Sorry. Yeah, I was confused. I was thinking that was 8,001, but yeah, it's not. Okay, so it's not in there. It's not in that range. It does not represent getting a 1. It would represent getting, if you think about it, getting whatever's in that row of 4. Yeah. This is analogous to using a table of random digits and doing 4 digits at a time from the table, as you can read about it in chapter 3. Let's finish with talking about simulating a continuous distribution. Maybe I couldn't give you enough information there to. What I could do is I could finish the spreadsheet after class and share it with you, and you can see what I did. It should be pretty intuitive. And I'll probably base your assignment based on my example. I'll give you an example with a probably binomial with a smaller value of n. Okay, so you don't have to end up lumping things together. The basis for simulation with continuous random variables is this fact that we proved here earlier today. X is an arbitrary, quote unquote, continuous random variable, at least with the monotone increasing CDF. And you'd find U to be this, then U is going to be uniform over the interval from 0 to 1. And what that means effectively for simulation is you use some random number generator, like on a spreadsheet, to generate a random number between 0 and 1. Oh, we're going to have time for today's spreadsheets. Use on a spreadsheet, use equals RAND. And I think you have to put parentheses with nothing in them to get a simulated value of a random variable capital U that's got a uniform 0, 1 distribution. Then, to get the simulated value for the X that you're interested in, we call the simulated value little u, then a simulated value of capital X, the random variable you're interested in, is little x equals capital F sub capital X inverse of little u. You're using the inverse function. We'll do an example pretty quick here. Example. Suppose X is exponential continuous distribution, exponential distribution with mean beta equals, say, 1,000. Yeah, I do want to do this example. This might be 1,000 hours. That's the mean. And this could represent, for example, lifetimes of light bulbs in hours. Say lifetimes of light bulbs in hours. Could I simulate values of this random variable? Is the question. If I'm going to use this method that I'm talking about here, I've got to figure out what capital F is. The PDF of an exponential random variable, the E means exponential here, is 1 over the mean, 1 over beta, times e to the negative x over beta. Beta is the common symbol for the mean in this context. So that'll be 1 over 1,000, e to the negative x over 1,000, or if you prefer, 0.001 e to the negative 0.001x for x positive. The CDF, it turns out, I'm going to write down without explaining, turns out to be 1 minus e to the negative x over beta, e to the negative 0.001 times x for x positive. That's the CDF. What's its inverse function? Let's call the output u. What's the inverse function of that? Well, you just got to solve it for x. Add e to the negative 0.001x to both sides and subtract u from both sides. Then take the natural log of both sides. Then divide both sides by negative 0.001, which is the same as multiplying by negative 1,000. And that is the inverse function, capital F sub capital X inverse of little u. Looks a little strange. Looks like its outputs might be negative. No, they're positive because u is between 0 and 1. ln of a number between 0 and 1 is negative. Multiply it by negative 1,000. This is a positive quantity. Let's quick use it on a spreadsheet. You got to use that formula like this. So I'm going to first use, and I'll finish an example like this in the spreadsheet before I share it with you as well. Put it over here. I can use equals RAND. Maybe you don't need parentheses. Oh, it needs at least one parenthesis. Equals RAND. I'll put the second one in there for me. Generates random decimals, real numbers, you might say, between 0 and 1 uniformly. I could copy and paste this to generate a bunch of such numbers. And then to generate sampled values for X, use this formula. Plug those numbers I just generated into the function -1000 times natural log of 1 minus u. Hang on here a second. This is what you do. Equals -ln of 1 minus, or -1000 times ln of 1 minus this thing. Every time you enter these things, by the way, those numbers change. There is a way to keep them fixed, but for the 0.24265, the output's 277.9. That light bulb lasted about 278 hours. You enter it, it gets changed, it gets updated always. Some of those are in the thousands. Some of them are less than 1,000. What's the mean of all those? I4 through I18. Well, it's not a huge sample, so I'm not sure how close it will be to 1,000, but it should be in the very rough ballpark of 1,000. 1,100 when it changed the numbers again. I was sampling from a distribution that was exponential with mean 1,000 when I do this. Okay. All right. Have a good day.